Well, yeah, today we have with us Professor.
Hello.
Yeah. Sorry, sir. Like the internet is the biggest problem. I guess
Okay.
he is having fluctuating internet. I mean, it is very problem here. Maybe I will give. Yeah,
It would be better, yeah.
yeah. I will give the intro then. Yeah. So, hi everyone. Welcome to the third talk of our online talk series. This time we have a very special guest, Dr. Nirmalya Kajuri from IIT Mandi. He is an assistant professor there. His main research area lies in quantum gravity, string theory, aspects of black holes, and its information paradox. And he is also quite a motivated science communicator. He will deliver this talk on black holes, a brief history. Over to him. Yes, sir.
Okay. Thank you, again. Thank you, 137 Inverse, for this invitation. Very happy to be here and talking to you about black holes. So my talk is titled Black Holes, a Brief History, and I will try to tell you a little bit about the history of black holes, starting from Einstein and coming up to Stephen Hawking's work on the black hole information loss paradox. One second. So black holes. So we often think of black holes as these mysterious objects, this kind of veils beyond which we cannot see. But black holes are also very simple objects. In fact, Chandrasekhar described them as the most perfect macroscopic objects there are in the universe. Because black holes, you see, are not built with anything. They're built with just space and time. So it's just space and time themselves that go into making these black holes. So what's very enchanting about black holes is they're at once the most simple possible objects being made only of space and time. At the same time, they're extremely complex objects whose mysteries we are still searching for answers for. So what was the history of black holes? This is the history of black holes in a nutshell. The theoretical possibility of black holes was known from 1916, shortly after Einstein discovered general relativity. Well, if you go back many years, there was an earlier scientist, John Mitchell, who had given the possibility of black holes back in 17th century, but it was a different idea. The kind of black holes that we now observe, the possibility of them was known from 1916. But nobody believed that black holes could be true, could be real. It was the physicists, the community of physicists, were completely against the idea. It took 40 years for physicists to be convinced that black holes had to be real, that they had to exist out there in the world. And then the first black hole was observed around 1971. And in 1976, the next chapter in the story of black holes came when Stephen Hawking showed that black holes are not so black. They give out radiation. Hawking's discovery gave birth to a paradox which remains unsolved to this day. So let us go through the history of black holes, okay? By the way, at any point, please feel free to stop me and ask questions. So black holes, to understand black holes, we have to know a little bit about Einstein's theory of gravity. Now, most of you would know, I think all of you would know, Newton's theory of gravity, which was given by Isaac Newton. And for many years, it was the correct explanation of gravity. This is the rule that gravity is given by inverse square law, and it is proportional to mass. So mass attracts mass by a inverse square law of distance. But shortly after Einstein discovered special relativity, scientists realized that Newton's theory could not possibly be correct because it was in contradiction with special relativity. And Einstein, of course, being the person who discovered special relativity, was the first to understand this issue. And he started working on developing the correct theory of gravity. And finally, after 10 years or so of work, he found the correct theory, which we now know as general relativity. So what does general relativity say? So in a very brief and a kind of vague and artist's impression of general relativity, so to speak, Newton's theory had said mass attracts mass. General relativity said massive objects curve the space-time around them, and other masses move in the curved space-time. Now, these another way of saying it is mass tells space-time how to curve, and space-time tells masses how to move. Now, this one line requires one semester of coursework to understand fully mathematically. So we'll just leave it at that. But let us get an understanding. Let us get at least a picture of how one works with general relativity. What is the nitty-gritty of working with general relativity? The heart of the theory of general relativity are these sets of equations called Einstein's equations. Usually when we hear the word Einstein's equation, we think of E is equal to mc square. But Einstein's more important equation are these field equations of general relativity. These field equations, which are shown on the right side, and you don't have to understand what these things are, what the symbols mean. I'll tell you what they mean. So this tells us how mass or energy, mass and energy are the same thing, as you know from relativity, how they curve space-time. So left-hand side, whatever is written in the left-hand side of this equation measures how curved space-time is. It's kind of a measure of the curvature of space and time. And the right-hand side measures the energy density of space-time. So if you have some matter, some planets or whatever electric field, everything carries energy. And this energy is what curves the space-time around it. And then you get gravity, which is a result of the curvature of space-time. So how does one work with this equation? Well, if I give you the energy density, then you can try to solve for the curvature. So the right-hand side is energy density. And if I tell you, okay, I have a planet which is maybe spherical and so on, which has this much mass, then that is telling you what is the energy density. And then you try to solve how the space-time is curved around this planet, and then you will get how the gravity looks. But this is very hard in practice to solve these equations. We know very few exact solutions of Einstein's equation can be counted on one hand. But the first solution was discovered by Carl Schwarzschild in 1916. So very shortly after Einstein discovered general relativity, Carl Schwarzschild became the first person to solve Einstein's equation. So how did he solve it? What he assumed was that there's some kind of perfectly spherical star or perfectly spherical massive object, and what is the space-time around it. So that he assumed a world where there is one massive object and there is nothing around it. Okay, there's empty space around it. So how will this one massive object, spherical object, curve the space-time around itself? And he solved with this input, he found the curvature of space-time. So this was his right-hand side, and he solved for the left-hand side, and he found how that space-time would look. Now the solution he found is called Schwarzschild solution. It describes the gravity outside a spherical body. Now there was a very curious thing that he found. He found that suppose you keep the mass of the spherical body or the spherical star the same, but decrease its radius. You keep the mass the same and you keep decreasing the radius, the size of the star. So you are making it more dense. And the result is that space-time will be more curved. Space-time around the star will get more curved, or in other words, there will be stronger and stronger gravity as you decrease the radius. After a certain critical radius, which is called Schwarzschild radius, remember this term, Schwarzschild radius, the space-time will become so curved that nothing can escape from it, or the gravity will become so strong that nothing, not even light, can escape from its field. So within that radius, within that Schwarzschild radius, the sphere of that Schwarzschild radius becomes a black hole. Nothing can escape from it. So strong is its gravity. Okay. Now, a small fun fact is that we usually think of black holes as extremely dense, but it does not need to be. The more the mass of the black hole, the less dense it can be. In fact, a 10 billion solar mass black hole has 1/10 the density of air. And this is may seem surprising, but it is true. A 10 billion solar mass black hole has just 1/10 the density of air. Now, Schwarzschild solution had some mysteries, and these mysteries are called singularities. There are two singularities in Schwarzschild solution. What is a singularity? These are regions where some parameter or some quantity seems to go to infinity. It seems like there are some infinities in the solution. Something becomes infinitely large. So it seems that usually when we get infinity as an answer, we know that we have made a mistake. Maybe we divided by 0 somewhere and made a mistake. And what are the singularities? One of the singularities is at the Schwarzschild radius. The other is at the center of the black hole. So Einstein was not happy with these infinities coming in answers, and he rejected the reality of black holes. He believed that this black hole thing, whatever the solution Schwarzschild had obtained, this possibility that Schwarzschild had shown, that if you have a lot of mass packed into a small enough radius, you will get a black hole. Einstein did not believe this to be true. Einstein thought it was just a mathematical thing that was coming from equations, but it could not be possible in the real world. He believed that there was no way that a black hole could actually be formed. He said, okay, maybe the solution is showing that, but can you actually make a black hole? And his argument was, you cannot make a black hole. He said he did not believe that any natural process could give rise to a black hole. And at some point he tried to write a paper proving this. Okay, so what do we know now? We know now that Schwarzschild radius singularity is not a real singularity. It's not a problem. It's just some choice of bad coordinates. Okay, we choose some coordinates. People then were working with some coordinate systems which just had a was not suited to the problem, which had a bad, which is a bad coordinate system, and it seemed to give answers which were infinite. But if you calculated any physical quantity, if you calculated anything, how space-time is curved, or what will an observer crossing the Schwarzschild radius see, you always get finite answers. The infinity is just a result of a mistake that we made, a choice that we made, which was choosing a bad coordinate system. So the singularity at the center is real. At that point, space-time becomes infinitely curved. Its curvature becomes infinitely strong. So it's like infinitely strong gravity. And of course, infinitely strong gravity doesn't mean anything. It means that your theory is wrong. If your theory is predicting infinity, you can never check that prediction, which means that there's something wrong. And this is still a mystery. It's still a mystery that what the singularity at the center of the black hole means and how one can resolve it. This is a place where Einstein's theory breaks down at singularities. So at the center of the black hole, Einstein's theory does break down, and we don't really understand what goes on there. We hope that quantum gravity will solve this mystery. Now, Einstein, as I was saying, rejected the idea of black holes, and because Einstein was the leader of the field, was the father of general relativity, most people used to follow him. And when he said this is not possible, a lot of people took it to heart and believed that it can't be possible. And Einstein's rejection set the field of black holes back to some extent, because no one took them seriously and no one almost was working on them. There was a strong belief that they could not be real. The next step in this story comes from the Indian physicist Subramanian Chandrasekhar. Subramanian Chandrasekhar was studying something completely different. In fact, he did not quite work on black holes at that point. He was studying the fate of stars that ran out of fuel. So you know stars run on nuclear fuel. And from that, they generate a lot of thermal pressure. So inside stars, we have gravity that pulls the star together. It tries to pull all the parts of the star close together, whereas pressure is what keeps the parts of the star apart. And when the star has nuclear fuel, when it is burning, it has a lot of thermal pressure. Eventually, that thermal pressure runs out. When the fuel runs out, that thermal pressure goes away, and there are only two forces left. One is gravity, which is trying to pull the star close, which is trying to squeeze the star, and the other is electron degeneracy pressure. What is this pressure? It comes from Pauli exclusion principle. When you try to push two electrons too close together, there is a pressure that develops, which is called the electron degeneracy pressure. As you know, two electrons cannot be in the same state by Pauli exclusion principle, as some of you may know. So this pressure is trying to push electrons apart when they try to be squeezed too much. So two forces, gravity, squeezing, and electron degeneracy pressure, repulsive. So it is trying to repel. And Chandrasekhar did a computation which showed that what will happen as the result of the fight between these two forces. Who will win? That is the calculation he was doing. He was doing it as a 19-year-old student. And he showed that mass of a star, if it is mass of this star whose fuel has run out, if it is 1.4 times greater than 1.4 times solar mass, then gravitational squeezing will win. Okay. So this is the graph that Chandrasekhar had. Look at this graph. So this is he's saying that this is density of the star versus pressure and gravity of the star. So as density decreases, the parts of the star come close together, and the gravitational force is slightly more, and that is drawn with these red lines. So all these red lines correspond to different stars with different masses, and these lines show how the gravity increases when density is decreased. And the pressure graph shows how its pressure behaves with density. So this blue line is the pressure, and the red lines are gravity. Now, for the star to be in equilibrium, these two forces must match. And you can see that when the mass of the star is below 1.5 solar mass, there are points where these two lines intersect, where the pressure and the gravity lines, the blue and the red lines, intersect. And those points of intersection are where you will get equilibrium. Those two forces are the same, so they will balance out. And you can see that for stars which are above 1.4 solar mass, so the 1.51, there is no point of equilibrium. So only stars which have less than that mass, when the nuclear fuel runs out, they will kind of start becoming more and more dense. But at some point, their pressure and gravity will balance out, and they will remain as white dwarfs. These kind of stars are called white dwarfs. But for 1.5 solar mass stars or greater, there is no point of equilibrium. So they will simply keep shrinking under gravity. That is what Chandrasekhar found, that there is no mechanism of stopping their shrinking, at least from this picture. Okay, at least when we talk about electron degeneracy pressure. And this is called eternal collapse. The star will collapse eternally because it will shrink under gravity without stopping. And Chandrasekhar's result faced a lot of resistance from the physicist community, the community of physicists and astrophysicists, because again, what was this really saying? This was really saying that the star should become a black hole then. Because if something shrinks without stopping, then it should become a black hole. And people did not like the idea of black holes. They were extremely resistant to it. So Arthur Eddington, who was a famous astrophysicist of the time, he was extremely against the idea. Arthur Eddington was known as the one of the great experts on relativity at the time. And there's a story that goes that when someone told Eddington that some journalist told Eddington that I have heard that there are only 3 people in the world who understand general relativity. Eddington replied that who is the third, implying that he and Einstein would obviously be in the list. So he was a celebrated doyen of the field, and because he was completely against the idea, everyone went against it, and Chandrasekhar had a very hard time convincing people that it was true. But eventually, after many years, people did come around and realize that his what he had done was correct. And in fact, Eddington had been wrong in thinking that this process cannot be true. So this was in the around 1930. The next step came from the man in the movie, Mr. Oppenheimer. Oppenheimer was in the 1930s. He was a professor at Berkeley, and he worked in a lot of different fields. He worked in several different fields with different students. And at some point, he became interested in the issue of black holes. And he wrote 2 papers on this topic with his students. Both are extremely important papers, Oppenheimer and Volkoff, and Oppenheimer-Snyder. So what did Oppenheimer get from black holes? So first, Oppenheimer-Volkoff. So at that time, people had come up with the idea of neutron stars. So this is idea where the core of the star is, instead of being like it's rich in neutrons. And neutrons, like electrons, have this degeneracy pressure. Neutrons also have, but it is higher degeneracy pressure. So this was, some people thought this was a way out of the eternal collapse problem, that there was a higher pressure, and it could be that this pressure graph we see here would be modified for this neutron stars, neutron cores, and maybe there would not be eternal collapse. Maybe for all black holes, for all stars, it would balance out. Pressure and gravity would balance out. So then the obvious question, which people did not ask, but Oppenheimer asked, was okay, there's some limit for electron degeneracy pressure. Stars with whose cores are mainly electrons. Is there a similar thing for neutron stars? And with his student Volkoff, he showed that even for neutron stars, there is a maximum limit. And if the star is above that limit, they will collapse eternally. Nothing can stop the collapse. So at this point, black holes seem kind of inevitable, that collapse at least will happen and nothing can stop it. So if that happens, we should get black holes. But it was still not clear what happens in the collapse. The process of a star collapsing into itself under its own gravity had not been studied. And this was Oppenheimer's next project with his student Hartland Snyder. And Oppenheimer and Snyder considered a simple model. Now, this is one of the things about doing physics, is that often when you want to describe something in the real world, it is very complicated. It's extremely complicated. There is, a lot of details. So in this problem, for example, this question, can quark degeneracy pressure exist and prevent the formation of black holes? Quark degeneracy pressure exists. Okay, let me come back to all the questions in the end.
Yeah, the questions will be answered separately in the question and answer argument. Meanwhile, people can keep asking the questions in chat section. I'll read those at the end.
Okay, great. Okay, so Oppenheimer-Snyder, as I was saying, that often in physics, it's important to make models which are very simple. You may have a problem which is very complicated, like in this case of the star collapse, there is this pressure, there's the internal forces. It's a very complicated process. But Oppenheimer and Snyder found a very simple model which captured all the essences of the problem. Now, physicists are often made fun of because people say that we work with spherical cows, but in this case, they work with a spherical model and it worked very well. The results it gave matches very well with the observations. So Oppenheimer and Schneider considered this simple model of a spherical shell of dust which was collapsing. So they ignored all the real world things. They just thought, let us just take some spherical thing like dust and let it collapse. Dust just means that we are completely ignoring its pressure. Okay, and so then they saw that when this kind of spherical mass, it keeps decreasing its radius. At some point, it crosses the Schwarzschild radius, and then a black hole would form. But the star would continue to collapse. There's nothing would stop the star from collapsing, and it would continue to collapse till reaching infinite density at the center, which is the singularity. In fact, the mathematical part of the computation had been done by an Indian physicist, Vishweshwar Dutt, a very short-lived Indian physicist, who was not looking at black holes, but he had solved the mathematical part of what Oppenheimer and Schneider were looking at, which is trying to solve the Einstein's equation, which you know is how we get all the answers for the case when something is collapsing. So there's an Indian connection here. However, Oppenheimer and Schneider were not aware of his work, and they did it independently. So this is the paper by Oppenheimer and Schneider, and if you have watched the Oppenheimer movie, this paper was in fact shown in the movie. This was Oppenheimer's greatest contribution to science, and unfortunately, it came in September 1, 1939, which is also when Hitler invaded Poland and the war started, and Oppenheimer was snatched away, and he wouldn't work on this field. And in fact, no one was working on black holes anymore. Even though this was the first time a black hole formation had been described. But this field was again kind of postponed. Work on this field was again postponed for a long time. In fact, even this Oppenheimer-Schneider collapse, although it showed clearly black holes forming mathematically, even this was not taken seriously by physicists at that time. What was their objection? They said it was too idealized. They said, this, you are considering a perfectly spherical object, you're considering it has no pressure, ignoring all the real world complications. And maybe these real world complications, when you consider them, will completely change your answer. So they said, okay, your answer may be wrong because you have ignored the real world. This is too idealized. We don't believe in it. And it was very difficult to convince people because, as I was telling you, doing these problems involved solving Einstein equations. So you have to solve these Einstein's equations, which are a set of coupled differential equations, and find out what happens when something collapses and so on. If you want to study collapse, you have to solve Einstein equation for that situation where something is collapsing. And that is a very hard thing to do unless you make these idealizations, unless you make these assumptions that the thing that is collapsing is perfectly spherical. Okay. So next comes another Indian connection, Amal Rai Choudhury. So again, Amal Rai Choudhury was not so much interested in black holes as he was in singularities. So these singularities were a topic of debate, and Amal Kumar Rai Choudhury, who was a junior scientist at the time, was interested in this topic. And he was kind of a person who had taught himself general relativity, and he wanted to work on it, although he was warned not to. So he was a junior scientist in the Institute of Cultivation of Science, and his boss, the great Indian scientist Meghnad Shah, told him that, this general relativity thing is too much removed from reality. No one works on it. You should not work on it. You should work on some atomic and molecular physics or something like that I'm telling you to work on, and otherwise you won't have a job here. So he was threatened to work on this. Nevertheless, he continued to work on his own thing in his free time, and he found a very important result, which is now known as Rai-Choudhury's equation. So Rai-Choudhury's equation the exact details are not important for us, but it is kind of shows how gravity tries to focus things to a point. And the importance of Raychaudhuri's equation comes in the for black holes comes in the subsequent work of Roger Penrose. So now we are in the 1950s. This is 15 years after Oppenheimer's work, and physicists are still skeptical of black holes. No one still believes that black holes could be real. And as I was saying, that the problem was that existing mathematical methods were not really enough to show how you can find realistic black holes. Very difficult to solve Einstein equations. Then comes Roger Penrose, and he brought tools from a field of math called topology. We will not go into the details, but this was a very powerful move. This was a kind of, so Penrose himself had a mathematics background. He came to physics and he brought with him these new mathematical tools of topology. And using this together with Raychaudhuri's equation, he was able to show that black hole formation was almost inevitable. Black holes would be very generic in the sense that whatever initial conditions you can have very different initial conditions and so on, you would still get black holes. Okay, so this was showing that situations may arise, the situation where things collapse into a black hole are almost inevitable. It can happen due to a variety of initial conditions. Okay, so it's not very sensitive to what initial conditions you have. Black holes can still form. So this, after Penrose's work, people were convinced that no, black holes must be real, because people were objecting that, if I change the initial conditions, if I change the star, if I change the shape of the star and so on, black holes may not form. But after this, there was very little doubt in people's mind that black holes were in fact inevitable. Okay. And the first detection of black holes, sort of detection, is usually regarded, Signus X1 is usually regarded as the first black hole detected. So how did we detect it? We found X-ray beams from this system. So the Signus X1 system is one where there's a black hole and there's a star. There's a black hole and there's a big star which are orbiting each other. Of course, we cannot see the black hole, we can only see the star. And what we actually observe are the X-ray beams from the system. So what happens here is that this black hole seems to be kind of sucking out the gas from the star, and this gas orbits the black hole and it gets heated up very, very hot. It becomes very, very hot, and it is concentrated in a very small region, and it radiates X-rays. When we get X-ray beams from a small region which is very, very hot, that is a signature that there is a black hole, because there is no other system that can heat up things that much while also kind of keeping them confined to a very small radius. So this was the first time we kind of detected a black hole, and now it's very generic. Now we have even taken pictures of black holes. Okay, so then we have Stephen Hawking. So the next step, next part of the story is the story of black holes with quantum theory. Of course, there's a whole story of detection of black holes and astrophysical black holes and so on, which I'm not qualified to tell you because I'm a theory person and my interests are more towards the radiation of black holes. So what was Stephen Hawking interested in? He was interested in the quantum physics of black holes. So far, what we have been talking about, we have not really talked too much about quantum theory. Interesting phenomena, which is called Hawking radiation. We found that black holes radiate out, or from around black holes, a radiation comes out, and this is called Hawking radiation. And this existence of Hawking radiation gives rise to a paradox, which remains unsolved. So I'm going to give you a description of this paradox using a very simple analogy. Okay, this is an analogy describing what the black hole paradox means. So for that, let us remember some basics from quantum theory. According to quantum mechanics, which I think all of you have studied, every object, every physical system can be associated with a quantum state. Some psi, some wave function describes every object. And the information of this wave function or quantum state is what we will call in this talk quantum information. Now, there are some situations where there are entangled states, where this information of a quantum state is collectively stored in two different systems or two or more systems. So when two systems are entangled, we have to have access to both to get the full information. If we don't have access to one of them, then we do not have the full quantum information. We cannot retrieve the full quantum state. We cannot know it. Okay, so this is the analogy that I'm going to use is of a jigsaw puzzle. Entangled state is very much like a jigsaw puzzle because you have to have access to both to get the full quantum information. If you don't have access to one piece of a jigsaw puzzle, you don't have the full information. You have to have both, and then you get the full info. And one of the principles of quantum theory, sacred principles of quantum theory, is unitarity. Unitarity says in this context that quantum information can never be destroyed or created. Quantum information cannot be destroyed. Information of a state can always be retrieved from the future. Another way of saying it in mathematical terms is the unitary operator can be reversed to give you the, you can find the inverse of the unitary operator to find what the state was earlier. So quantum information cannot be destroyed. Okay, so let us run with this analogy of a jigsaw puzzle. Now, black hole radiation. What Stephen Hawking had shown is that not only do black holes radiate, but this radiation is entangled with the inside of the black hole. This radiation is entangled with the inside of the black hole. So what does this mean in terms of our jigsaw puzzle analogy? This means that one piece of the puzzle, whenever a Hawking radiation is emitted, whenever a photon is emitted, what happens is that photon, that Hawking radiation, is entangled with the interior of the black hole. So it is as if one part of the jigsaw puzzle is radiated outside, another part of the jigsaw puzzle remains inside. Radiate one part outside, one part inside. And as more and more radiation goes out, there are all these jigsaw puzzle pieces, the red pieces which are outside, and there are these blue pieces which are inside. So if I'm someone who is outside a black hole, obviously I have no access to the inside of a black hole. I cannot see what is inside. I have access to only partial information. I don't have the full information. I don't have all the pieces. I have only the red pieces, not the blue ones. This is not a paradox. This is not a puzzle. Remember the principle of unitarity only said that information cannot be destroyed. It did not say that information cannot be hidden. What is happening here is simply that some information is hidden from us. We don't have full information, but that's not a problem. That's not something that contradicts unitarity. However, what happens is as black holes radiate, they lose energy. It is radiating, it is giving out photons, it is losing energy. And as it loses energy, it shrinks. So energy is mass, so it loses mass and it shrinks. So as the black hole shrinks, as the black hole radiates, it shrinks in size and it keeps shrinking. We don't know any reason why it would stop shrinking as it radiates. So what's happening? So let's look at these pictures. So in the first picture, there are some Hawking radiation, red bits outside, some red pieces outside, some blue inside. In the next picture, the black hole has shrunk in size and it has made more Hawking radiation. So there are a lot of these red pieces, red puzzle pieces which are outside and a lot of blue ones inside. So the amount of hidden information inside the black hole has gone up. And finally, if nothing stops this evaporation, and we don't know why it should stop, black hole should simply disappear completely. It should be gone. And then it would evaporate, like water evaporates as it radiates. And similarly, this black hole should completely evaporate and disappear completely. And this is the problem. If it disappears completely, all the blue pieces inside it are also gone. And we are just left with the red jigsaw puzzles. So now we cannot complete the puzzles because only the red pieces are left. Only half pieces are left. And this really means that information has been destroyed. Information has been destroyed. We cannot complete the puzzles. And this is a violation of unitarity. So what we have here is a paradox. We have unitarity, which is a sacred principle of quantum theory. And we have a situation with the black hole, which seems to be saying that if we take it to its logical conclusion, that information should vanish and unitarity should be violated. Now, what could need to happen to save unitarity? It should be a picture like this, that at some point, so initially, the earlier picture, there are red pieces outside and blue pieces inside. Now, to save unitarity, somehow, it should happen that the blue pieces start leaking from the black holes. They start coming out from the black holes at some point before it completely disappears. And then it should happen that before the black hole completely disappears, all the blue pieces are outside, all the info is leaked out. And in the last picture, you can see them joined with the red pieces. And this is saying that there is no missing information. All the puzzles are solved, all the information is outside, and unitarity is saved. So this would be a scenario where unitarity would be saved if there was some mechanism by which information could leak out of black holes before it completely vanished. However, if we want to do this, it turns out that this can only happen by violating some other principle like, there should not be any accelerated distance and such. So without violating some very core principle, we cannot have this. So the black hole information loss paradox is really a tension between unitarity on the one hand and the other sacred principles like locality and principle of equivalence. And this remains to this day unsolved, although there are some interesting new ideas which claim to be possibly solving it coming from string theory. Okay, so I will stop here with the summary. What we saw in this talk, hopefully, is that black holes are both very simple and very mysterious. And the history of black holes has this lesson for us that sometimes absurd sounding ideas like black holes, like something, trapping light in space-time, these absurd ideas can also be real. And we should keep our minds open to ideas which initially sound very strange. And even great people like Einstein can be wrong. So we should not put too much store on the words of the great scientists. Open questions remain: how to solve this black hole information loss paradox, and also how to resolve this singularity at the center of the black hole. We don't know how to solve it. It is saying that general relativity breaks down at that point. We would like to find an answer. Okay, so with that, let me end this talk. Thanks once again for inviting me, and we can have the question session now.
Thank you for delivering the talk. Yeah, now question sessions. Shashank had one question: can quark degeneracy pressure exist and prevent the formation of black holes?
Yes, so in quark stars, there are certain stars called quark stars for which that can happen, yes. But again, there's a particular circumstance in which quark stars can happen, but it's not true that black holes can be indefinitely stopped. In fact, now we know that black holes are true. Of course, we have not observed any quark stars, but theoretically, it's definitely a possibility.
There is one question. There are actually two questions. One is nothing crosses Schwarzschild radius. So from which point are the radiations radiated? And the second question is, if the red pieces and blue pieces are entangled, then we should have complete information. Please clarify this.
Okay, so let me answer the first question. Sorry, what was the first question again? Nothing crosses Schwarzschild radius. No,
Yes.
that is not first.
Which
That's
point are the
okay.
radiations radiated?
Okay, there are two different points here. First of all, yes, things can cross Schwarzschild radius. It's not true that nothing crosses Schwarzschild radius. Anything can cross Schwarzschild radius. If you were, for example, sitting on the star which collapsed, you would cross Schwarzschild radius. And if you're an observer who wants to dive into the black hole, you can. You can always cross Schwarzschild radius and go inside. The confusion is probably because if an observer outside, far away, is looking at you, crossing the Schwarzschild radius, from their point of view, they would never see you cross the radius. They would never see that someone crossing the radius. From their point of view, it would seem that it takes infinite time to cross the radius. However, from your point of view, if you're an observer who dives in a black hole, you will cross the radius in finite time, in very small time, in fact. And this difference is a kind of very amplified case of something you might have seen in special relativity, which is time dilatation. So just like in special relativity, different frames have different notions of time. The same thing happens here. An observer who is at rest with respect to the black hole, an observer who is moving into the black hole, have very different notions of time. And so in one frame, the person would never see anything cross the black hole. And in the other frame, the person who is actually going into the black hole will cross it in finite time. And the second part of the question is, where does Hawking radiation come from? It comes from outside the black hole. It does not go from inside to the outside. It comes from outside of the black hole. I mean, the calculation one can do is like check the energy density outside the black hole, and one can see that there's depending on the wavelength of the radiation, it will come from some region outside of the black hole. So what happens is the presence of the black hole causes the region outside of it to give away radiation. Okay. Actually, let me start the video.
Another part of that question was, if the red pieces and blue pieces are entangled, then we should have complete information. Please clarify this.
If I do not understand this question, you can unmute yourself and clarify what you
ask
mean.
the question, can unmute and clarify. I mean, what do you want to ask by that?
But let me say this.
Yeah, he is unmuted.
Okay.
Yeah, you can ask.
It's okay.
You can directly
Yes.
ask.
Yes.
Yeah. So in this slide, hello.
Yes, I can hear you.
In this slide, if the red pieces and blue pieces are entangled,
Yes.
and if only the red pieces come out,
Yes.
then we will have some information about the blue states also, because of entanglement.
Yeah, the idea is that, if you have, for example, so let's take an entangled state. Okay, let's take an entangled state, which is entangled, has two pieces. Okay, so now if you don't have access to the, so let's say a system is entangled between two states. There's a system of two parts, A and B, and it is entangled, and you have only access to B. Okay, so then you cannot find what the state of A is. All your observations on A, you can only make measurements on A, and they will be described. They can be described by what is known in physics as a reduced density matrix, which is something that you obtain by tracing out you start with the density matrix of the full system and trace out the system that is not observed. And that traced out density matrix or reduced density matrix will explain all your observations. So in other words, you don't need to know, you cannot know the full details of A, and all your none of your measurements will reflect the full details of A. Now, what you are talking about is, if I make a measurement in A, I will know immediately what I would get if I made a measurement in B. Okay, so that's a different thing. But what you cannot know is what the state, what exactly the full state is. So in other words, by making a measurement on A, by making any number of measurements on one part of the system, you would never understand what the full system was, because all of them would be consistent with a number of different possible entangled states, not a single unique one. Does that help in answering the question?
Yeah, it's fine.
Yeah, so the next question is, what do you mean when you say that black holes are made of only space-time? Can you roughly give an idea?
Yes, so the idea is that black holes being made of only space and time, when we describe black holes, we simply describe them by the space-time geometry. Okay, so there is no, so once the star has collapsed, once it has gone to the singularity at infinite point, there is nothing else. It's only space and time which are curved in such a way not to let anything out of them. So there is no, there's no matter, there's no box that is forming the space-time, that is forming the black hole. It is just space and time curved in a way that does not let things exit, things escape. And yet a black hole, even though it is formed of just space and time, it has properties very similar to that of matter, just like it radiates, like with something we did not talk. So it radiates means it has some temperature. And something we did not talk about in this talk is we can also find some entropy of black holes. So black holes have all these properties of macroscopic systems, like entropy, like temperature, like it can radiate. However, what is there in the black hole? It is just space and time curved in itself in a way that does not let things out. Okay, so that's what is meant by, that's what Chandrasekhar meant by saying that black holes are the most perfect objects. In other words, when we describe black holes mathematically, we just describe the space-time. We don't have to give you anything about what the matter is, where atoms are, what is the density of atoms, and so on.
Okay. Next question is, from a black hole, how does radiations come out? I guess this question is answered. I guess so.
Yes. So, I mean, if you want to, there is no simple answer to this question. You simply have to do a calculation of quantum field theory in black hole space-time, and mathematically it pops out. Now, there are some simple kind of analogies why this happens, but mathematically, the only real answer is you have to compute this and find it.
Yeah, the next question is that, are there certain recent arguments which say that Hawking's argument for the paradox were incomplete?
I mean, there have always been arguments that Hawking's arguments are incomplete. And recently, there has been some progress in this direction coming from the what is known as the ADS-CFT or holography, the ADS-CFT correspondence, which is something that comes from string theory. And there is the idea is that that these things that we saw that in this picture that we saw that these cannot escape, and they completely shrink in size and disappear. This does not happen. What happens is that this information can in fact be kind of teleported, you might say teleported through a wormhole, sort of, to a different location. So what happens is locality is violated in the sense that something goes far away almost immediately, and that saves the information loss paradox. Now, Hawking's argument is kind of incomplete in several senses, but let me not go into that detail. What the modern computations seem to be showing for some particular toy models is that there are particular toy models in which the black hole information loss paradox is indeed solved, and that the information does come out. So these toy models are showing that information does come out. But whether these toy models apply to our real world is still an open question, because directly don't, but whether the same kind of thing happens in the real world is what people are still trying to find out.
So there is one question. So it is just the space-time curved in some manner, but as you said that it is a matter that curved space-time. So are black holes objects?
Well, I mean, if you want to call space, it depends on the definition of objects then. So, excuse me, if you want to call space-time as objects, then yes, black holes are objects. They are formed of, collapse of matter, and they can also be formed of, in the far past, they could have been formed of quantum fluctuations of matter. They can be formed not necessarily of planets, but of very different gases. But once the collapse happens, what we have what is left is just the space and time. To the extent that we don't know what happens to the matter inside, they all seem to go into the singularity.
Okay, so there is another question. Recently, a connection is being drawn of quantum information theory with black holes. Quantum complexity is being used to describe black holes. Is there some work going on regarding this paradox as well from information theory point of view?
Yes, a lot of recent work in holography draws connections of, this holography theory has in itself connections with information theory. And there's a lot of recent work that goes on, has been going on in exactly what you are talking about, in connecting the theory of information with the theory of black holes, and asking questions like how information can leak out of black holes. So the answer to the question that, sorry, what was the question again? Is there some connection between information theory and black holes?
And is there some work going on regarding this paradox as well from information theory point of view? Recently, a connection is being drawn of quantum information theory with black holes. Quantum complexity is being used to describe black holes.
I mean, the quantum complexity part is something people work on. Let me leave it at that. But the point here is that there is connection between information theory and so in quantum information theory, there is something called quantum error correction, where which shows how you can send a message in a way that it's protected against errors. Okay, you can send some quantum. So quantum information theory is a lot about sending information in a way that it can be deciphered and so on. And quantum error correction is a part of it, which says that how you can send a message with where you can have some errors, but you can still decipher the final message, even if some errors creep in due to noise or whatever other reason. And there are some definite connections between quantum error correction, how that works, and how black holes kind of maybe saving information. So there's some kind of strong connection between that, but the details are quite technical. So yes, there's a definite connection here.
Yeah, so there is another question. If a particle is accelerated at the speed of light, will it form black hole as its mass would be infinite, or it's just with stars?
I mean, you cannot accelerate a particle to the speed of light. That is not something you can do, right? So you cannot. So that's not possible because you simply cannot do that. Anything massive can never reach the speed of light. You can only approach the speed of light. But yes, you can have situations where something that is very fast, something like something called shock waves, can create black holes.
Okay, so these are all the questions in chat. So I personally have one question. So when you talk about, I mean, combining the quantum theory and this general relativity to solve this paradox in usual sense. So do we always assume that the basic foundations of quantum theory is correct and then move forward, or it might be that some other interpretations of quantum theory might give some other solution, probable solutions to the information paradox? I mean, what exactly is being done?
Yes. So, for example, if you look at, I mean, it's not an assumption. Everyone is like different people are working on different kind of approaches to this. So, people who work in string theory, for example, takes the quantum foundations as is. So it does not modify, string theory does not modify quantum theory in any case. It finds gravity as part of a certain quantum theory, a quantum theory of strings. So in that approach, there is no no modification of the foundations of quantum theory. Now the question about quantum interpretations, that there are different interpretations of quantum theory, but none of them change quantum theory anyway. They're just different ways of interpreting the formalism of quantum theory. You are not going to get as such unless you directly modify quantum theory. If it is just an interpretation, you are not going to get different experimental predictions from them. You are going to get different ways of understanding the same experimental predictions. So different quantum interpretations, to my knowledge, do not give you different possibilities for black holes. And if they do, they won't just be interpretations. There would be something more than that. There would be modifications. If some modification of quantum theory is true, we don't know. But again, someone has to propose a modification which is found to be consistent. And so far, we don't have that. Something that is consistent with observations and can also solve black hole information loss paradox. I'm not aware of the existence of such a proposal.
Okay, so this is the end of the question and answer session and end of the talk as well. Yeah, thank you, Dr. Nirmalya Kajuri, for delivering the talk. Thank you, sir. Yeah.
Thank you. Thank you for having me. Okay, so I'll log off now.